Worksheet number 7 starts off with an interesting question. Here we're given a balanced chemical equation with known amounts of each of our reactants, and instead of being asked to figure out how much product we make, we're asked to take a look back at the reactants when the reaction's over and figure out how much of our excess reaction we have left over at the end of the reaction. So I put together a few steps that will help us go through this problem. The first step is going to be to find the limiting reactant. This is going to be important because we have to know how much of the aluminum oxide we make. And once we know then what our limiting reactant is, we also know inherently, by the way we calculate it, how much product we made. So the product is our aluminum oxide. Then we can use the amount of product that we made to figure out how much excess reactant was used. So whichever one of these we have in excess, we can use the amount of product we made to figure out how much of the excess reagent was consumed. And then from that, we can figure out how much of it was left over. Thankfully, step number 4 is the easy part, but getting to step number 4 can take a little bit of math. So let's go through this process. First of all, let's find what the limiting reactant is. So we're going to do this just like we've always done it in the past. I'm going to move this up a little bit, but you'll be able to tell what I'm doing here. So let's look at our oxygen. For oxygen, we have from the problem we had 2.31 moles of oxygen, and from the balanced chemical equation we made 2 moles of aluminum oxide and consumed 3 moles of oxygen. So our moles of oxygen cancel, and what we have here is 1.54 moles of aluminum oxide. Okay, and let's check the aluminum. We had 1.73 moles of aluminum, and from the balanced chemical equation, once again, we had 2 moles of aluminum oxide that are produced when 4 moles of aluminum are consumed. Moles of aluminum cancel, and we have 0.865 moles of aluminum oxide. Okay, so which one of these did we run out of first? We ran out of the aluminum first. So that tells us that aluminum is the limiting reactant. Okay, so step 1 is done. And then also we've already done step 2. Step 2 was determining how much product we made. Well, there we go. Right there is step 2. So step 3 says, find how much excess reagent was used. So let's go back now to the chemical equation. And we have used up all of our aluminum, because the aluminum was the limiting reagent, so that's what we ran out of. So we have no aluminum left, so our excess reagent is going to be the oxygen, so we want to figure out how much oxygen do we have left over at the end of the reaction. And the first step to doing that is going to be step 3. It's figuring out how much of this did we use at the end of the reaction. So let's do that down here. So we made 0.865 moles of aluminum. So we made 0.865 moles of, moles of aluminum oxide. And now we can use the balanced chemical equation to convert this into how much oxygen was used. So let me bring this back up. we have just a mole-to-mole ratio. We have 2 moles of aluminum oxide were produced when 3 moles of oxygen were consumed. And that's what we're interested in, is how much oxygen was consumed. So we made 2 moles of aluminum oxide and we consumed 3 moles of oxygen. So that's the mole-to-mole ratio we want to use. So let's come back down here, and we have 3 moles of O2 are consumed when 2 moles of aluminum oxide are made. So you notice now we're going backwards. We're going back to the reactants. So our moles of aluminum oxide, that's our product, so they cancel, and now we're in moles of O2. Okay. So if I do this out on my calculator, I get 1.2975 moles of oxygen. So this is the number of moles of oxygen that are, are consumed. It's very important. That's how much we consumed. Alright, so now let me bring you back up to here. Originally from the problem, we saw that we had 2.31 moles. To start off, we had 2.31 moles of oxygen. So we figured out how much we used, and now we can figure out how much is left over by saying, okay, well, we used about 1.3 moles. So if I take how much I started with and subtract from it how much I used, I should be able to figure out how much I have left over. So now I'll bring you here, and we can do that mathematically. So we started with 2.31 moles of oxygen, right? So this is what we began with. Now we want to subtract from that 1.2975 moles of oxygen. This is how much we used, or how much we consumed. The amount that's left over is simply going to be the difference between these two, which is 1.0125 moles of O2. This is what's left over at the end of the reaction. So now that I'm in moles, I just have another simple unit conversion where I go from moles into grams, because that's what the question's asking. Right? The question's asking how many grams of reactant do we have left over. So I've got 1.0125 moles of O2, and now I just want to convert it into grams, so I'm going to do that by saying that 2 times 15.999 grams of O2 per mole of O2. Remember, we had the 2 here because we have 2 oxygen atoms in a molecule of O2, so we have to double that mass. And if I do this on my calculator, I would discover that I made, or I'm left with 32.4 grams of O2. And so that corresponds to C. So the right answer for number 1 is C. Okay, for number 2, I'm being asked to determine the percent composition of a molecule called sodium benzoate. That's this molecule here. And I went ahead and looked up on the periodic table and found that the molecular weight of this molecule is 144.11 grams per mole. This problem is exactly like all the other percent composition problems we've done. There's absolutely no difference. So I'm just going to go ahead and sort of run through this one a little bit more quickly. I'm going to say that for every 1 mole of this molecule, I have 1 mole of sodium. So 1 mole of sodium is found in every 1 mole of sodium benzoate. And then from the periodic table, I get 22.989 grams is how much a mole of sodium weighs. My moles of sodium cancel, and so I'm left here with 22.989 grams of sodium per mole of sodium benzoate. Okay, so now percent composition for sodium is just going to be this mass. So I got 22.989 grams of sodium divided by the molar mass of this molecule, where it's just 144.11 grams of sodium C7H5O2 benzoate. So all I'm saying here is how much of this molecule is sodium. That's all I'm saying here. So I've got a mole of sodium here and a mole of the molecule. And so in a mole of the molecule I've got 1 sodium, and I'm just saying, okay, well, how much of the total mass of this molecule is sodium? And what I find is, if I do this math, is that it would be 15.95% sodium. So by mass, that is the portion of the total mass of this molecule that is sodium. So for number 2, it's a little bit more difficult now because I have both A and D that can be the right answers according to this, because both A and D have 15.95% sodium. So I have to do one more element to elucidate which one of those is the right one. And I'm going to go ahead and do carbon, just because that's the next one that's available. So there are 7 moles of carbon in 1 mole of sodium benzoate. Right? That's because it comes from here. I have 7 atoms of carbon in every 1 molecule of sodium benzoate, so I'm going to have 7 moles of carbon if I have a mole of this molecule. So I'm going to convert that to grams of carbon. So my moles of carbon cancel. And I'm going to go ahead and include my percent composition calculation in here. For some of you, this might be actually a little bit easier to see than to have it separated into steps like that. So then I'm going to say that for 1 mole of sodium benzoate, I have 144.1 grams. Okay. So this way we can see how our units actually cancel. Now our moles of sodium benzoate cancel, and the units that we're left with are grams of carbon per grams of total of the total molecule of the sodium benzoate. So this way we can say the percent composition is 12.011 times 7, right, because we had 7 of them, grams of carbon divided by the total molecular weight of the molecule. Okay, so what we're saying here is that this is going to be the total mass of carbon in a mole of this molecule. And if I do that, I would discover that this is going to be 84.077 grams of carbon. So it's going to be approximately 84 grams of carbon in a mole of sodium benzoate. And then if I just do this, because I remember that a mole of benzoate here weighs 144.11 grams, I'm going to find that my percent composition for the carbon is 58.34%. And now we can say with certainty that the correct answer is D, because D is the only one that has 15.95% sodium and 58.34% carbon. So the right answer for number 2 is D. Number 3 gives us this chemical equation here, and it's already balanced. And this kind of a reaction is called a precipitation. The reason it's called that is because lead 2 chloride here, when it forms a solid. It's insoluble in water. So it precipitates out, and that's why we call it a precipitation. So the problem gives us the number of grams of lead and the grams of potassium chloride that we have, and it also gives us the actual yield of lead 2 chloride that we produce. And the goal is to determine what the percent yield of this reaction is. So I went ahead and went to the periodic table and calculated the number of moles of lead and moles of potassium chloride that we have, just to save us some time. And the first step to any sort of a problem like this, where we're trying to find the number of moles of product that we make, is to determine which reactant is going to run out first. So that's going to be our limiting reactant. So let's find the limiting reactant. Okay, so let's get started with the lead. So for the lead, we have 0.124 moles of lead. And using the balanced chemical equation, we can see that 1 mole of lead is used up to make 1 mole of lead 2 chloride. So our mole to mole ratio here is simply 1 to 1. We just write it like this. Now our moles of lead cancel, and we are in moles of lead 2 chloride. I like this kind of mental math. This is great. This is just 0.124 moles, but now instead of lead 2 plus, it's lead 2 chloride. Okay. Now let's take a look at the potassium chloride. Let's see if this one is going to be our limiting reactant. So we start off with 0.382 moles of potassium chloride. And now it's no longer a 1 to 1 mole ratio. Now for every 1 mole of lead 2 chloride, we need 2 moles of potassium chloride. So I got that just from the balanced equation, right? So I need to use up 2 moles of potassium chloride to make 1 mole of lead 2 chloride. Okay, and that's all that this is showing. So I'm going to make half as many moles of lead 2 chloride, right? And unfortunately, this is not exactly the mental math I can do, but I did it ahead of time, so there's nothing to worry about. So with 0.382 moles of potassium chloride, I'm going to produce 0.176 moles of lead 2 chloride. Okay, I'll leave the question up to you. Which one of these is the limiting reactant? Well, that's going to be this one, right? This one here is our limiting reactant. So it's the lead. The lead is our limiting reactant. That's going to mean that we're going to run out of the lead first. So let me bring this down. So the lead is the limiting reactant. Okay, and now we also know how much lead 2 chloride we made. So we can just use this quantity here to tell us how many grams of lead 2 chloride we made. So that would be what we would consider our theoretical yield. So let's go ahead and do that. 0.124 moles of lead 2 chloride. And if we're converting into grams, we need the molar mass. So, or the molecular weight. Both of those terms are used synonymously. So a mole of lead 2 chloride is going to weigh 278.106 grams. Okay, so now our moles of lead 2 chloride cancel, and we are in grams of lead 2 chloride. This gives us 34 point, I'll just round, I'll say 34.5 grams of lead 2 chloride. So what do we do with this number? Well, we got to remember that the equation for percent yield is the actual divided by the theoretical. So our actual came from the problem that was 29.4 grams of lead 2 chloride. That was how much we actually made when we went and did this experiment in the lab. And how much we were supposed to make had the reaction gone to 100% completion was 34.5 grams. So what percent yield is asking is how much of that did we recover? How much of that did we get? And if I do this out, I would find that the percent yield was 85.2%. So the right answer for number 3 is D. So let me just also really quickly address number 4. We already determined what number 4 is, which is why I really like this method. And we needed to determine what number 4 is in order to do number 3. So if you did number 3 this way, you would conclude that lead is indeed your limiting reagent. Here the question calls it reagent, but I like to be extremely specific and say that this is the limiting reactant, because if you look at the chemical equation here, these are your reactants and these are your products. So when we're talking about something over here on this side of the equation, I like to call it the limiting reactant. Although you could get by with either term. Anyway, so lead is going to be our limiting reactant, and therefore the answer for number 4 then is A. Number 5 involves a combustion analysis of an unknown hydrocarbon. So here's our unknown hydrocarbon, and by hydrocarbon what we mean is that the unknown molecule contains only carbon and hydrogen. And when we combust this molecule, we produce some water and some CO2. You notice I'm not worrying about balancing the equation, because what we're more concerned about is the actual quantities of CO2 and water that we make. So the problem gives us that we have 0.697 grams of water and 1.55 grams of CO2. I went ahead and converted these into moles, just using the molar masses of the molecules. And from here we can determine the amounts of carbon and hydrogen that are produced in this reaction, and be able to relate those back to the composition of the unknown molecule. So how are we going to go about doing that? Well, the first thing I would do is I would start out looking at the carbon. So I've got here, let's find the amount of carbon in CO2. Why do we want to do CO2? Well, because it's the place where we have all of our carbon, and by the conservation of mass, we know that the amount of carbon that we have on the right side of the equation, on the products, has to equal the amount of carbon that we started out with on the left side in our reactants. And since we know that the only source of carbon here is from the unknown, then we can figure out how much carbon the unknown had if we know how much carbon is made, or how much carbon dioxide is made on the right side of the equation. So we just use conservation of mass to figure out from a known amount of carbon in the products how much carbon the unknown reactant had. So we got here, we can find the amount of carbon in the CO2. We know we have 0.0352 moles of CO2, and we also know that in 1 mole of CO2, there is 1 mole of carbon. So our moles of CO2 cancel, and now we're left with moles of carbon. Alright, so let me move up a little bit. Now we're interested in finding the amount of hydrogen in water. So we're looking at our products here, and the only place where we see hydrogen is in the water. And this is really great because we know how much water we end up with, and again, by the conservation of mass, we also know that we can relate that directly to the amount of hydrogen that was in our unknown molecule. So let's do that. We had 0.0387 moles of water, and for every 1 mole of water we had 2 moles of hydrogen. Moles of water cancel, and here we have 0.0774 moles of hydrogen. So now that we have our moles of hydrogen and our moles of carbon, we can construct an empirical formula. So now we can make an empirical formula. So we have 0.0352 moles of carbon and 0.0774 moles of hydrogen. Just like with any other empirical formula, what we can do first is divide these coefficients, divide these numbers here, by the smallest number. So the smallest one of these two is going to be the one with the carbon. And what that's going to provide for us is just 1 with the carbon, and then the hydrogen has 2.199. Well, we are clearly not done. We're not at the integer phase yet, so let's take this and multiply it by some number, and we can try 2, 3, 4, 5. Could do anything really. This is just sort of a matter of trial and error, but the number that would get you the closest to an integer would be 5. So if we take these and we multiply them by 5, we would get C5H11. It turns out that when you multiply 2.199 by 5, you get something very, very, very close to 11. And then you just look at that and it's like 10.998, I think. And you just look at that and go, well, yes, of course that rounds up to 11. So if you just did that, then the answer you would get is C5H11. And that corresponds to B. So B is the correct answer for number 5. Number 6 asks us to determine how many moles of calcium chloride, that's this here, how many moles of calcium chloride are present if we have 175 milliliters of a 0.465 molar solution of calcium chloride. So the first thing I would do for a problem like this is I would remember, what does this M mean? What is molarity? So let's define molarity here before we go any further. Molarity is the moles of solute divided by the liters of solution. So it's the moles of solute divided by the liters of solution. So when I see that I have 0.465 molar calcium chloride, what I'm saying here is 0.465 molar calcium chloride is just 0.465 moles of calcium chloride dissolved in 1 liter of solution. That's all I'm saying. So I've got 0.465 moles of calcium chloride in 1 liter of solution. So the last thing we need to do is consider that we actually don't quite have a liter of solution. We only have 175 milliliters of solution. So what we can say is that 175 milliliters is just 0.175 liters. Because you remember that a milliliter is 1,000th of a liter. So I just multiply this by that unit conversion, and I would find that I have 0.175 liters. Hopefully you remember that. I just assumed that that was something you would remember. Anyhow, so now we have only 0.175 liters instead of a liter. Well, if you notice here, we've got the same units, so maybe we can multiply these together in such a manner that they will cancel, and we'll be left with moles, which is what we're looking for. And in fact, that is exactly what we're about to do. So we have 0.465 moles of calcium chloride, right, in a liter of solution, times 0.175 liters, because that's how much we have. Now our liters cancel, and what we're left with is the number of moles of calcium chloride. And if we do this, it leaves us with 0.0814 moles of calcium chloride. So what I said here is that if I had a 0.465 molar solution of calcium chloride, and I had only 0.175 liters of it, or 175 milliliters of it, I would have in that 175 milliliters 0.0814 moles of calcium chloride. So the right answer for number 6 would be A. Number 7 tells us that I have a stock solution here of 0.375 molar potassium nitrate. And I need 5 grams of potassium nitrate. So how many milliliters do I need to use of this 0.375 molar solution? And the answer may not seem intuitive unless you recognize that what you can do with the grams is just simply convert them into moles. So let's do that. We have 5.0 grams of potassium nitrate, and let's convert that into moles. 1 mole of potassium nitrate is 101.1 grams potassium nitrate. So my grams of potassium nitrate cancel, and now we are in moles of potassium nitrate, which is 0.0495 moles of potassium nitrate. So this is how much we need. And why did we convert into moles of potassium nitrate? Because if we remember, the definition of molarity is moles of potassium nitrate per liter of solution, right? So we're given the molarity of potassium nitrate. We are given that we have 0.375 moles of potassium nitrate per liter of solution, right? So if a liter gives me 0.375 moles, how many liters do I need to only give me 0.0495 moles? So this isn't unlike anything else we've done. It's quite similar actually, just with different units. So we need 0.0495 moles of potassium nitrate. Okay, and a liter, 1 liter gives us 0.375 moles. So if our moles can cancel here, we can figure out how many liters we're going to need that will give us 0.0495 moles. So if we do this calculation, we would determine that we need 0.132 liters of this solution. So since the question is asking us to express this number in milliliters, we just have to recognize that there's 1,000 milliliters in a liter, and so we just do the conversion here, and this becomes 132 milliliters. So the correct answer for number 7 then is D. Number 8 asks us to determine how many grams of solute do we need in order to prepare 1.4 liters of 2.1 times 10 to the negative second molar sodium hydroxide. So let's take a second and recognize that sodium hydroxide here is our solute. So when we're talking about the solute, we're just talking about the sodium hydroxide. And let's also kind of clean this up a little bit, because I get confused when I see scientific notation everywhere where I personally don't think it needs to be. This number is just 0.0210 molar. Okay, so now we're working in cleaner numbers. If this was maybe times 10 to the negative 9th, maybe I would feel like that was more necessary. But here we've just got 0.0210 molar. Nothing too unusual. So we've got 0.021 molar sodium hydroxide, and we're looking to make 1.40 liters of this solution. We want to figure out how many grams of sodium hydroxide do we need in order to do this. So let's take a step back and remember what the definition of molarity is. So when we're saying that we have 0.0210 molar sodium hydroxide, let's remember that what we're saying is that we have 0.0210 moles of sodium hydroxide per liter of solution. Okay? And now that we have a moles per liter expression, and we know the volume of the solution we want to make, and that's in liters, then what we can say is just a liter is going to require 0.021 moles of sodium hydroxide. That's what the molarity tells me. But I want to make a little bit more than a liter. I want to make 1.4 liters, so I got to have a little bit more sodium hydroxide to still satisfy this concentration. So I'm going to multiply this by 1.4 liters. Now my liters are going to cancel, and this will tell me how much sodium hydroxide I need in order to make a 0.012 molar solution and 1.4 liters of it. So my liters here cancel, and this means I'm going to need 0.0294 moles of sodium hydroxide. Okay? So if I want to make 1.4 liters of this solution, I'm going to need 0.0294 moles of sodium hydroxide. And since the question is asking us to determine the number of grams of sodium hydroxide we need, we just simply convert this mole quantity into grams. From the periodic table, a mole of sodium hydroxide weighs 40 grams. So my moles cancel. And if I plug this into my calculator, I would find that I need 1.176 grams of sodium hydroxide. So that rounds very closely to 1.18 grams, which gives you the answer C. So the correct answer for number 8 is C. Number 9 gives us a stock solution of 12.0 molar hydrochloric acid, and asks us to determine how many milliliters it would take of stock solution to prepare 4 liters of 0.5 molar hydrochloric acid. So the approach that I use for problems like this is to use the equation M1V1 equals M2V2, which you might be familiar with from lecture. But I would like to introduce you to a little bit more of a general equation, and it's written as C1V1 equals C2V2. So instead of the M's we have C's here, and what the C's represent is just concentration. So this is to say that you can use any kind of concentration here. It can be molarity, it could be parts per million, like ppm, it could be parts per billion, which is ppb, where you might be looking at maybe chlorine levels in a pool, for example, or something like that. You could use any sort of concentration. It doesn't have to be molarity. So the same equation works for situations like that, where you've got different units for the concentration. But the key thing to make sure is that regardless of what your concentration units are, the units for C1 and C2 have to be the same. And the same thing for volume here with V1 and V2, the units have to be the same for those as well. So we'll see that play out as we use this equation to answer this question. So over here, let's say that the C1 and the V1 are going to describe the stock solution, and that the C2 and the V2 are going to describe the dilute solution. So let's see what we know so far. C1, for the stock solution, it's the concentration is 12.0 molar. V1 is what we're trying to find out. We don't know what V1 is, so we're going to use all of this information up here to figure out what V1 is. C2 is the concentration of our diluted solution, which is 0.5 molar, and V2 is the volume of our diluted solution, which is 4.0 liters. So what we want to do is we want to solve for the volume, and the way we're going to go about doing that is going back to this equation and algebraically solving for V1. We're going to do that by dividing both sides by C1. So V1 equals C2V2 over C1. Alright, so all I've done here is I've just divided both sides by C1. And now let's plug in our numbers. C2 is 0.5 molar, and V2 is 4.0 liters. And we're going to divide that by C1, which is 12.0 liters. Oops, excuse me, molar. It's a concentration. So we have molars cancel. So remember how I mentioned that we just want to make sure that the units for the concentrations and the volumes are the same? This is why. So when you do something like this, you want to make sure your units cancel. So the molars cancel, and we're left in liters for our volume. So V1 then becomes, if I do this out on my calculator, 0.167 liters. Okay, and since the question asks us to determine this quantity in milliliters, we just want to re-express this as 167 milliliters. So we're going to need 167 milliliters of this stock solution if we want 0.5 molar HCl and 4 liters of it. So this is how much of the stock solution we would need. So the answer that corresponds to then is B. So the right answer is B. In number 10, we are told that the average concentration of sodium chloride in the ocean is 350 milligrams per 10 milliliters. So what I did here is I went ahead and converted 350 milligrams into grams. So I've got 0.350 grams of sodium chloride. And what it's asking us to determine is the concentration in molarity. So let's remember here that molarity is moles of solute per liters of solution. So we have two things we need to determine. We need to figure out what the moles of solute are, and we need to figure out what the liters of solution are. So we have sodium chloride as our solute. So what we need to do is go from grams of sodium chloride into moles of sodium chloride. So let me do that here. 0.350 grams of sodium chloride times, for every 1 mole, I have 58.443 grams. So my grams of sodium chloride cancel, and now I am in moles of sodium chloride. So I'm done there, and the number this gives me is 0.005989 moles of sodium chloride. And now the last thing I need to figure out is the liters of solution. So I had 10 milliliters, so I'm going to go ahead and convert this into liters because it has to be in liters. So for every 1 liter, there are 1,000 milliliters. Milliliters cancel, and this tells me that I have 0.01 liters of solution. And the solution here is our ocean water. So I have two quantities that I need now. I have the moles of sodium chloride and the liters of the solution. So the molarity is going to equal 0.00598 moles of sodium chloride divided by 0.010 liters of solution. And if I do this out, I would find that I get 0.599 molar sodium chloride. And what that corresponds to then is B. So B is the correct answer for number 10. Alright, and that was worksheet number 7.